Okay, coming back, we are going to skip the chapter 7 to 9 because we plan to take only one lecture to cover the core features of those units from pump to turbine to boiler. So I would love you guys read the textbook first, and then we come back to those discussions. Otherwise, it's quite easy to get lost what would be the topics of those chapters. So I will have the reading assignments out, and I'm not planning to assign the whole 3 chapters for your reading. I will pick up a few topics of each chapter, those main and the key points of those features. And after our reading, we plan to have the discussion next Tuesday on chapter 7 to 9. This is why we skipped the order, and we will have some discussion today on also a very important concept, which is chemical potential. So I would love to have this really quick review to make us really proud of the progress. I think my iPad does not work very well today. It's not following the slideshow. I think we're not going to have too many notes for today, so I'm going to move back to the PowerPoint on my laptop. So I'll try to figure out what's going on for the iPad. So let's try to switch back to the PowerPoint. Are you guys seeing the PowerPoint?
It looks
Not
like they're
yet.
loading.
Yeah, it's asking me to press the escape key to cancel. Okay. How about now?
Yes.
Yeah.
So let's have a quick 5-minute review on the things we have already discussed. So first of all, we were really focusing on lots of discussions on the energy form. So that involves the work, the heat as energy input to make changes of the system. And we shall be able to provide some examples of the work, which is the mechanical work, PV work, heat. You can think of lots of examples as long as the subject is going to change the temperature, reactions, separations. Whenever you are going to change the temperature of the system, then it must involve some heat release or heat uptake. And the difference is, as we know that work can 100% convert into heat, but heat cannot otherwise. That will be the violation to the second law of thermal. And we had a discussion on the second law to look at what is the maximum conversion from heat to work, which is determined by the Carnot cycle efficiency, right? So when we are trying to convert heat into work, then we need to have at least 2 reservoirs working in 2 temperatures, T high and TC. That will determine the efficiency of the conversion. So that is the first slide, or the first thing I want to have a quick discussion. And then, of course, we've discussed the first law of thermal. We have introduced enthalpy and entropy, internal energy, and some other energy functions as well. We have 4 energy functions depending on which shall be the 2 control parameters to use. So we are going to have the internal energy, enthalpy, Helmholtz energy, and Gibbs energy. We also discussed the difference and the connections between path and state functions. So the general rule is if we try to calculate the path function, we try to convert that calculation into the state function. We may take the difference between the internal energy and the work to calculate heat, right? So that is the general philosophy for those calculations. We have a big chapter 4 on heat capacity. Especially, we try to understand the heat capacity dependence on temperature. So there's one function using the coefficients, and we can express the heat capacity as a function of temperature. And also, when you take a look at this CP and CV, I hope you still somehow recall For the ideal gas, we have a very nice equation to correlate Cp and Cv. So Cp is Cv plus the gas constant R, but that equation is only valid for the ideal gas. And along those discussions, we also had some uh, confinement. For example, we need to understand what is the open system, what is the uh, closed system, and what is the isolated system. So when we have the open system, we are looking at the mass and energy exchange. So we allow both mass and energy. When we have closed system, molecules cannot move inside or out of the system, so we can only exchange uh, energy with the surrounding. When we have the isolated, then there's no energy nor mass exchange with the surroundings. So typically we are using that three models to describe and understand the concepts. Uh, for the reality, of course, we are always dealing with open systems, but we can always simplify the open system to other corresponding systems. We had some discussion about equilibrium, especially in chapter 4 when we try to calculate the heat import. We quickly realize that if this is a phase transformation, say ice is melting into liquid water, then our knowledge from whether Pecan, from Mohi Wang, or general chemistry tells us that the energy import will be completely utilized to drive the phase change of the system. So the temperature will remain the same. There we call this is the equilibrium. And we also need to recall the phase law. Phase law is one of the one of my favorite equations in any topics, because that is the guiding equation to tell us how many parameters you have to study in order to receive the complete understanding of the system. So if you recall the equation, it's f the independent the degree of freedom independent parameters should be c minus help me, c minus what, c minus pi. Pi is the number of phases plus 2. 2 uh, represents the temperature and pressure of the system. So that is the equation to use. Thanks to Gibbs. And then we also had some slides on the phase diagram. We try to have the three-dimensional phase diagram, and we hope to receive two-dimensional projections so we can understand the PV dependence or PT or TV. And along that line, later in the chapter 6, we were also looking at the other potential diagrams. So whenever we have diagrams, they are supposed to help us have a quick understanding of the system or to correlate the numerical values. So we have the so-called temperature entropy diagram. We have this log entropy versus pressure diagram or other diagrams you can prepare and manipulate. So those diagrams are very useful when it comes to real life application. So this is all those things we have discussed. And of course, we had some math fun on equation of states. We started with the ideal gas equation. We moved on to account for the deviation from ideal gas to real. Van der Waals proposed the two parameters A and B, and he constructed the so-called Van der Waals equation of state. And that equation will be in the cubic of volume, so we also call his equation as the cubic equation of states. And then other scientists along the years, they have also proposed other ways to account for the molecular size and intermolecular interactions. So we have a family of those cubic equation of states. And we were also talking about the very nice idea of virial equation state using the uh, Taylor series expansion, right? So if we understand the ideal gas, then we use that understanding to derive the Taylor series expansion around the ideal gas, and then we can have those virial equation states. And in the experiments, as we discussed in the lecture, we are able to manipulate the equation and come up with a plan to do the measurement so that we can have the values for the second and the third uh, coefficients we will need in the virial equation state. And then we also had another angle of those equation states. Uh, that is still from Van der Waals discussion. He realized that if we are not using the absolute temperature and pressure, but we try to take the absolute value with respect to their critical values. So we have this so-called TR, PR, and VR. Then we are going to have those reduced units. Uh, and we quickly realize that as long as those species, uh, if they can be described by those uh, reduced units, then there's only one equation to describe all those species. So that is how we come up with the theory of corresponding states or corresponding principles. Along that discussion, we have the two parameter uh, thanks to Van der Waals, and we have the three parameter thanks to Pizza, where we try to correlate the eccentric factor omega, and we try to use the saturation pressure of the substance, try to look at the deviation. There's one specific requirement at TR over 0.7, something. I cannot memorize the equation, but those would be the core concepts of three parameter corresponding state principle. Moved on, like we said, we had the three laws of thermodynamics, and along the discussion of the, excuse me, the second law of thermodynamics, two major components. One is the Carnot cycle of the of the four units. The other is the definition of a new state function named entropy. And also looking at the last item on the entropy, we say entropy change using the ideal gas as an example. So that leads to one other very popular concept. In thermal, whenever we define something, whenever we derive the equation, we always try to utilize that equation on some simplified cases. So we always try to test the concept or the equation on the ideal gas and then move on to see what change will be required if we need to use the concept or equation to the real gases or mixtures. So that is always from a simple toy model to some realistic discussions. So that pattern has appeared again and again in our previous discussions. And then the most recent discussion of chapter 6, we had those components of, first of all, we were looking at the energy functions so that we know the internal energy, the Helmholtz energy, entropy, and Gibbs energy, what would be their corresponding two parameters, two independent parameters for each of the energy functions. And then along that direction, once we receive the full derivative of those equations, we utilize the partial derivative second order, and we receive the Maxwell equations. So the power of Maxwell equations would be we are able to convert any complicated term involving entropy. We're able to convert that into measurement of PVT terms. So again, the concept here is we try to convert those hard, complicated measurements into easy ones, relatively easy ones involving PVT. And we also discussed the residue property. The residue property involves one imaginary state. That is, we have this realistic high temperature high pressure, and we cannot really assume the system will be at the ideal gas state. But we just try to see what would be the deviation if we do want to assume the ideal gas behavior. So this is why we have this concept of residual property, and we derived some equations to use if we need to calculate the property change, or you can use the diagrams and tables to look up values so that you can uh, perform the calculation. So those would be the discussion so far. So you can see that I was planning to use 5 minutes, but I end up using more than 15 minutes on those, right? So we do have covered lots of interesting stuff from the past 6 chapters. So what's the plan moving forward? Let's have a quick discussion on those plans. Nothing special, but only one keyword: mixtures. We're going to look at the mixtures. So when we talk about mixtures, that could be the gas-gas mixtures. We can have two components, two species, and they form the gas mixtures. Or we can stick with the pure gas, one component, but we are going to have liquid and vapor simultaneously in the system. So we need to look at those mixtures and understand why they are important, and what kind of new concept, new equations we need to derive in order to completely describe the system. And what would be the connection of those discussions to the previous lectures. Uh, so I have a list of those interesting systems when we are looking at the change of species, change of phases. So we can think of two examples. One is purely with the help of energy, we're able to drive the liquid into vapor so we can manipulate the phase change. The other is on the last line of the slide, we can also create and organize the reactions in order to have the, excuse me, have the different species and their corresponding different phases. So in order to make a change and manipulate the mixture, we can utilize phase equilibrium and chemical reaction equilibrium. So we are going to discuss some new concepts. Today's lecture will start the first one called chemical potential. And then we will look at the so-called fugacity and activity and also related coefficients. Those concepts are a little bit abstract at the very beginning, uh, but I hope to explain those concepts clearly to you. And we will also discuss about the solution models. So this is, if you try to run the analogy with the gas phase for the gas, we can always think of the reference, which is ideal gas. So the comparison would be always real gas versus ideal gas, and what would be the deviation from ideal gas. Here we are going to have the same type of discussion for the liquids. We are going to have the so-called ideal solution model, and for real liquid mixtures, we try to see what would be the deviation from the ideal solution model. So this will be the discussion we will have. So uh, for the following 2 units, nothing special. We firstly we try to understand some concepts, try to look at a few equations, and then we will move on and discuss the phase equilibrium and reaction equilibrium. After those discussions, I think the semester will be over, and we are ready to celebrate the holidays. So let's move on to see what is the uh, standard description to equilibrium. Let me try to recall all those terms. Uh, so when we have the equilibrium, meaning there's no change, the system is not moving to the left, to the right, and we are not going to have any net driving force. We are still going to have the interactions, but they will cancel each other out in the driving force, so there's no momentum for any further change. Let me try to call this. Okay. So here I have the examples of driving force. So we could have the following driving force you can think of. The temperature gradient will be the driving force for the heat transfer, right? If we have the temperature difference, then the heat flow is always automatically from the hot to cold. If we are going to have the imbalanced mechanical forces, then there will be work. So heat and work will be the driving force. At the same time, we are going to have the mass transfer. And the mass transfer will be driven by the chemical potential, the concept we will discuss in a minute. So whenever we look at the equilibrium or not, we need to look at the driving force. And when it is a discussion of the driving force, we try to see what would be the resources of the driving force. So we would have three different driving forces in general: mechanical, temperature, and mass transfer related driving forces. So we need to look at driving force and each of them, each of the three. So here is a quick review on the phase equilibrium. So if we start with the phase diagram, let's stick with the point A, where according to the diagram, we are in the vapor phase, right? So if you try to maintain the fixed temperature, so that would be the isothermal processes. So if we are going to maintain the temperature, but we try to do some driving force manipulation, then we are able to push the superheated vapor into the liquid vapor equilibrium at B. Uh, Over there, we are going to have the phase transformation moving from B to C, right? We call that at point B, we are going to have the first liquid. And then moving all the way to point C, we will typically say that we are going to lose last bubble of the phase, meaning there's no vapor after state or point C. Then after point C, we will be in the liquid phase. And if you further compress it with the mechanical force, then at point D, you're going to transform the liquid phase into the first solid crystal. And over there, you're going to have, again, the phase transformation moving from D to E. And up to E, you're going to lose the last liquid. So over here, you're going to have a pure solid phase, and then you try to manipulate, further compress the solid up to the final state of interest. That would be the state F. So that is one typical way of utilizing the three-dimensional diagrams. It sometimes challenges us and requires a good imagination when we look at the three-dimensional diagrams. And also this is the more familiar two-dimensional PT diagram, where we need to identify at least two interesting points. One is the triple point. Recall that we discussed that triple point is the property of the system because there's no degree of freedom. There's no zone left for us to manipulate the triple point. Once we know the species, then the triple point is determined over there. And we also need to quickly recall on the critical point. I hope you still recall the three equations we can use at the critical condition. So that is the general thing for the phase diagram. So when we look about the phase diagram, say now we are trying to describe the liquid and the vapor equilibrium. So which energy term to use? We have four different choices. We have the internal energy, we have the enthalpy, we have Gibbs energy and Helmholtz energy. Here I have the website to ask you to read and have a quick understanding why people would often call this as Gibbs free energy or Helmholtz free energy, where that freedom is coming from. So try to pay some attention and take a 5-minute reading of the link I provide to understand what is free. So here is again the PT diagram. I don't know why I have it over here, but it's good to have another quick review on those. So especially for this one, when we have the PV diagram, I hope that you could run some exercise to understand where is temperature. So if we have the PV diagram, the temperature will be coming from those curves. And in the past, we had a discussion, say we are going to move the liquid all the way up, right? And we try to understand what would be the change of the system, what is the ratio between the liquid and the vapor. Using level rule, we are able to understand what is going on, whether they will disappear simultaneously, or we are going to have a remaining vapor or liquid phase by the analysis. Just try to look at those understanding and some working equation for us. So first of all, I'm not planning to really derive what would be a proper descriptor for the phase equilibrium. I simply explain that when we have the phase equilibrium, we are monitoring the temperature and pressure change. So if this is about temperature and pressure, then using the four derivative equations to the four energy equations, we quickly identify the Gibbs energy is a function of temperature and pressure. So this is why moving forward for the phase equilibrium, for all those discussions, we are going to use Gibbs energy for our discussions. So this is the first note of this slide. The second note is, as I have over here, at a phase transition, molar or specific values of extensive thermodynamic property will change all of a sudden. We don't have a continuous smooth change, but the only exception is the Gibbs free energy, which is for the pure substance. We try to define our discussion in the simple model system, one pure species. And if you are looking at the Gibbs energy change, then we will not have any change, nothing at all, for the Gibbs energy at the phase transition. So that is just the statement from me for two things. One is the Gibbs energy is the descriptor moving forward. The second is if we are looking at the phase equilibrium, which is happening right now, which is, for example, for the I hate to move back, but if this is the phase equilibrium, right? So any point on the line, we are having the equilibrium, because if this is the system, we are going to have the corresponding liquid and the corresponding vapor. And if we manipulate to move the point, to move the system along that tie line, then we are still having the phase equilibrium. So what this slide says that if we are having the system on the line, then the Gibbs energy does not change. Why and how? That can be easily explained by this equation. So this equation is coming from where? Coming from the chapter 6, where we were talking about the energy equations, the four energy equations. From the definition, which is G is H minus Ts. There's no need to memorize this equation. I happen to memorize this, and I hope this is correct. So if we move forward to take the fourth derivative, then replace dH by the previously derived equation for enthalpy, then we are able to receive this equation. So now when you look at this dG, the change of Gibbs energy, if the temperature is not changing, dt is 0. If the pressure is not changing, dP is 0. Then of course the Gibbs energy will not change, right? So that is a quick discussion on the the Gibbs energy change is when we are having the coexistence of liquid and vapor. When we are having the system on the tie line, then there's no Gibbs energy change. In other way, if we have dg equals 0, and at the same time we are having the two different phases, one is the liquid, the other is the vapor, then according to this equation, we can quickly arrive at this equation. That means the Gibbs energy of the liquid shall be exactly the same for the corresponding vapor phase. So that is the other agreement that we can quickly have. Then I try to introduce one other statement. So it says the equality of the molar or specific Gibbs free energy, which is also named as the chemical potential of each phase, will be exactly the same. So that is nothing special, but now we are moving from Gibbs energy and we try to add some limitation. This is the specific, or this is the molar based. And then if that is the case, so if the Gibbs energy is not the total, but it's molar based, kilojoule per mole for the species, then we can replace that molar Gibbs free energy using another different name as chemical potential. So that is the statement. Let's try to take a look at the sort of official definition. So in thermodynamics, chemical potential, also known as partial molar free energy. We will have the discussion on the partial part. Molar, this is the total free energy. You try to divide that by the number of moles for that specific species, then you have this molar free energy. It is a form of potential energy that can be absorbed or released during a process, whether it's a phase transition or chemical reaction. When we think a little bit more, just a little bit more of the potential energy, what is the potential energy? The potential energy we can easily think of if we are moving the water. Say I have a cup of water, then if I move the altitude, then I'm having a larger potential energy. This is the macroscopic potential energy. For the microscopic of potential energy, the potential energy is coming from intermolecular interactions. So molecules are not alone in their phase, whether it's gas, liquid, or vapor. They're always having some type of interaction with its neighboring molecules. And that interaction, the energy due to those intermolecular interactions will be recognized as a potential energy. And if you try to separate molecules from the liquid phase to the vapor phase, then you are going to make changes to their intermolecular interactions. And the change will be released, like we described here, be absorbed or released during that process, whether it's just a physical phase transition or a chemical reaction to further separate those atoms, not only the molecules. So that is the microscopic understanding of those energy forms and how they will be absorbed or released during the process, chemical reaction or phase transition. So let's try to have a quick review on the four energy equations. So those would be the four derivatives of the energy terms. So here we are going to utilize the Gibbs energy, or sometimes we call this as Gibbs free energy. Nothing special, but simply because the Gibbs energy is the function of T and P. But while the other equations, they are either the entropy, volume, or temperature, volume for Helmholtz. So we've defined the chemical potential in the previous slide, but we need to have some working equation. So this is again the pattern of a new concept. And as a result of the new concept, we need to have some equations. So that is introduced by looking at this. Now we have a system that say that try to have the general discussion to demonstrate that the chemical potential concept is a universal concept to any system, whether it's open, closed, or isolated system. So if we start with a homogeneous open system, and we can see that the each system is open to exchange. That is why it is open to exchange molecules, to exchange energies. So now the number of moles for each phase, say we are going to have M1, M2, and up to the M phase, Mary phase. So there we need to, if we want to completely describe the system, now if we are using the internal energy, which is a function of entropy and volume, except for entropy and volume, we need to describe how many molecules in each of those phases. So here n is the number of phase. Not easy to write, but I'm trying. So if this is the case, then we need to revise the previous equation for derivative, right? So now if you want to take the full derivative of the internal energy, du is a partial derivative with respect to entropy. So we have to take the partial derivative with one of each parameters. So we have many more over here and plus 2. So if we are looking at the partial derivative, then we try to maintain the volume and all those species, the number of moles fixed. And we move on to take the second partial derivative, dV. Over here, we try to keep the entropy and the number of moles for all those phases fixed. And then we have to use this summation because we are going to take the number of m partial derivative with respect to each phase. So this is we have to this I is moving from 1 to m, and we take the du over dmi. Over here, we need to keep the entropy and volume fixed, and we need to keep the other components fixed. If we are looking at the first phase m1, then m2, m3, m4 up to m, the number of moles over there shall be fixed. Here is the explanation. Mi means all the nj, all those other components are fixed while we are looking at the mi. So once we have this for derivative for the modified open system or for the modified phase equilibrium system, then we define this is the equation of chemical potential. We have this symbol of mu. So mu I is defined as the internal energy partial derivative with respect to the corresponding component or the corresponding phase over there. Okay, so now if we try to replace the partial derivative by the newly defined chemical potential, then we have this du term. Du is TdS. So this is the previous equation. Here we need to revise and add the contributions due to the existence of multiple phases. So that is the revised fundamental energy equation for the open system, right? So this is the first one. And if you think about the choices of other energy terms, you could easily come up with the same idea. What if I use H? What if I use Helmholtz and Gibbs? then you are going to receive the first part is still from the previous discussion for the one component pure phase. And then we just need to revise, we just need to add the contribution due to the existence of multiple phases or multiple components. So this is why we need to involve those other terms. And here, chemical potential is the one we just derived. And when you think about what is the physical meaning of chemical potential, nothing special. It's coming out of the contribution, the energy contribution to the existence of those different species or those different phases. Pay attention that I'm trying to convince you that we have two different ways. One is if you are having a liquid mixture, say one phase liquid mixture, then those different liquid molecules will make a contribution to the energy. The other case is we have one component but multiple phases. Then those different phases for the same component, they will also make a contribution to the energy. So no matter how, we just need to evaluate the energy term with respect to that specific component or specific phase. And that is the definition of chemical potential. All right. So now if we have revised the four energy equations, what's the plan next? So again, this is the summary term of the chemical potential. It's up to us which energy equation to use. I have a specific note. Let me change the color. Blue is the favorite one. So I have a note, and please pay attention to the note. And please come back to this slide when you are reading the textbook. I believe it's chapter 10.3, where we are talking about partial. So this is the first time we now include the name into the equation. So we have the mu I is the partial derivative of Gibbs over mi, Tp, and Ni, and we have a different note. We have a head to this Gi. G is the Gibbs energy. I is either it's the phase, it's the ice phase, or it's a component of I in the mixture. And the head means partial. So partial is the head in terms of the notation. And I want to add that partial, if you have the partial property, I may take a minute to write it down, partial. Let's say any property, we call this as a partial property. PROP. So the definition of partial property, whether it's partial volume, whether it's partial Gibbs energy, or partial internal energy, or partial enthalpy, or partial entropy, any property of partial is defined at temperature, pressure, and Ni, which means any of the partial property, they are the function of temperature, pressure, and composition. This is very important because now if you look at the chemical potential, we have four different ways of expressing this chemical potential. However, that is not qualified to be called as partial Helmholtz energy, simply because we don't have the right requirement. So here, the chemical potential in terms of Helmholtz energy we need to maintain the temperature, volume, and composition as the parameters. So that is not qualified to be called as the partial Helmholtz energy. And of course, we cannot call this as the partial enthalpy. This is not partial internal energy. Okay? Only this Gibbs energy, we are deriving the chemical potential with respect to the requirement of partial property. This is a little bit confusing, but I would strongly encourage you to come back to this slide while you are reading the textbook. In other way, we do have this partial, let's say partial. Let's look at the component I, Helmholtz energy. Like I mentioned, this shall be the function. If I try to express this as a general function, this shall be a function of temperature, pressure, and composition of all those I components. Okay? So that is very similar to the most recent discussion. You see that we try to put forth the request. We try to have the H enthalpy as a function of Ts, right? No, Tp. Although the enthalpy itself, by the pristine definition, it's the function of entropy and pressure. But we can, with the help of math, we can derive the equation, and we manually put the entropy as a function of temperature and pressure. Here is the very similar idea. If we try to understand the Helmholtz energy indeed, then we can try to write down this equation. Over there, we are going to take the partial derivative with respect to each of the terms, so that we can have the expression of the partial molar Helmholtz energy. So this is the quite important slide. I highlight so that you come back to this slide when you try to understand the partial molar property. So moving forward, what is the use of the chemical potential? We've defined the system of multiple components or multiple phases. We've introduced the idea of chemical potential, which is nothing special, just the energy partial derivative with respect to components or phases. We will derive the 4 equations to express the chemical potential. Then what's the use of it? The use of it is now we have the criteria to determine whether the system is at equilibrium or not. By the way, the only joy or the only advantage of the Zoom meeting is I can drink some water during the lecture. I think I never have that opportunity when it's the in-person class in the classroom. So let's try to see the use of the chemical potential. Now we have the answer, and again we don't try to derive those equations to convince you, but here comes the answer. If I have the 2 phases, let's try to look at the one component, 2 phases, alpha and beta. Well, we could have multiple components. We have component of I, but only 2 phases. When I can say that the system is at equilibrium? Well, you cannot say that until you satisfy all the 3 sets of equations. The first equation is when you have the alpha phase and beta phase, their temperature is the same. So if this is the case, then there's no heat flow, right? The second is when the pressure of the alpha phase is exactly the same as the beta phase. And if that is the case, there's no mechanical force, no driving force at all for the system. The system is the box, the container is our system. In our system, we have 2 phases, and each phase will have a number of Mary components. And the third equation we have to satisfy is now if you look at each component, if it's say we have oxygen and CO2, CO. So if the system of oxygen, CO at two phases, if they are at equilibrium, then I have to satisfy that the chemical potential of oxygen in the alpha phase should be exactly the same of the oxygen in the beta phase. And I need to also satisfy the carbon monoxide, the chemical potential in the alpha phase will be exactly the same as the chemical potential in the beta phase.
This is only when it's at equilibrium?
Yes.
Okay.
Let me try to add the chemical potential sign. So that is when we receive this, then we can call my system is at equilibrium. If you see temperature gradient, if you see still pressure gradient, if you still see that if oxygen in the alpha phase of the chemical potential is greater than the chemical potential of the oxygen in the beta phase, even you have satisfied the carbon monoxide, but oxygen is not at equilibrium, then the whole system is not at equilibrium. So we have to make sure all the components, all the phases are completely satisfied. Okay? So that is the mathematical definition of phase equilibrium. We were talking about the driving force. The net driving force should be zero for both heat, mechanical force, and mass transfer, which is the chemical potential gradient. But if one of those is not at equilibrium, then the system is not at equilibrium. So that is the definition of or the criteria of phase equilibrium. So again, I have this equation provided over here. Now, if we are going to have not only two phases, we are going to have multiple phases. Let's say we are going to have vapor, we are going to have the liquid of low density, we are that looks weird. Low density. We are going to have the other liquid phase of high density. High density, high rho. Then if we have three phases, then you need to satisfy, now you are moving and extending the criteria to multiple phases. You have to satisfy all the temperatures throughout those phases. They are exactly the same. All the pressures for all those phases, they are exactly the same. For any component, you are going to have exactly the same chemical potential to all those phases. So there you have to check on multiple equations for all the components, all the phases. And when you are satisfying those equations, then truly the system is at equilibrium. Okay, so that is the mathematical way to monitor and to determine whether the system is at equilibrium or not. So let's try to see moving forward, how do we utilize that chemical potential? Because although we understand that now I have a system, let's say a system of liquid water and and vapor water. I can measure temperature, I can measure pressure or monitor pressure. How do I measure chemical potential? That's not easy because that's energy related with the species. So I need to think of an easy way to monitor or measure chemical potential so that I can come back and tell you whether the system is at equilibrium or not. So I hope you see that now here the question is, we have a practical question. We understand that the system can be judged by the three sets of equations: temperature, pressure, chemical potential. But in reality, chemical potential is an abstract concept we could not easily measure or monitor. So we need to derive the equation so that we can use the derived measurements to reflect the chemical potential change. So that is what we try to achieve in the following slides. Let's move on. In order to have that discussion, let's try to limit our discussion into this much simpler case, and we can easily extend that to multiple components, multiple phases. So here, let's try to look at this two phase at equilibrium. And we moving forward, we are only focusing on chemical potential, and we assume that temperature and the pressure can be easily taken care of. So let's try to have our focus on chemical potential term. So for these two phases at equilibrium, we know that at equilibrium we shall satisfy the chemical potential will be exactly the same in the two phases. But the challenge, like I mentioned, is chemical potential is not easy to visualize or easy to measure. So there we need to replace chemical potential in the calculation using some other terms. Moving forward, we will talk about fugacity, activity, and activity coefficients. So those, although they look also awfully abstract, but I show you that in a few minutes we will have equations to look at the fugacity, look at the activity, and together with those coefficients we can easily measure those quantities, and we can have the understanding of chemical potential. So let's move on. Here comes the first equation or statement. Number one is the chemical potential. We are able to convert that into PVT. Now we have this X. What is X? Remember that when we talk about the phase diagram, the molar diagram or the other type of diagram, we were looking at the ratio of liquid and vapor. Those would be the X values. So that is the ratio of liquid and vapor. That is the first statement. The second statement is even better. We are able to have this equation, which is the chemical potential. Now you try to write this as mu chemical potential I. If we have mu I as a function of P V T X, then we should feel very happy about it. Why? Because PVT and the ratio of liquid or vapor, those can be easily measured in the lab. So if this is the case, if I have a function, then of course I can know the value of corresponding chemical potential. And I give you the gift, which is, I tell you that is always valid. Saying, when we take the partial derivative, because now if you try to measure mu I, naturally you would think of the fourth derivative like we have utilized a few times. We try to take the fourth derivative and we try to understand the dependence of chemical potential on pressure, chemical potential on volume, chemical potential on temperature, chemical potential on composition. And we have this surprising result when we try on the first partial derivative, which is if we are going to look at the temperature and component. So this is the component. So if we try to take the partial derivative of pressure while keeping the temperature and the composition as a constant, then we realize that is the corresponding partial molar property. First of all, let's check on the partial property requirement: temperature, pressure, composition. That is required to define this partial volume, okay? So if this is the partial volume, then we can replace this partial derivative by a head, okay? And the result says that, well, the chemical potential of that component with respect to only pressure change will be exactly the same as the partial molar volume. So that is the conclusion. Here I have another note trying to remind you that the chemical potential, we only have one equation called partial molar Gibbs energy. And that equation is indeed very helpful to derive the conclusion over here. I know that you guys don't like proof or math, but there's no way we can avoid those. Otherwise I have to force you to accept those concepts, and that's not a quite enjoyable process on your side, right? You would be always curious to see why I can tell you that partial molar volume now is related with this new derived chemical potential. So let's try to take a look at. So here comes the proof. That let me call all those slides so we can take a look at all those. So it's not awfully complicated. It's just so this is the equation we try to prove. That is the equation we try to prove. Then when we start with the chemical potential, when we are limited by the partial molar property requirement, we only have one choice to replace the chemical potential by a partial molar property, which is the Gibbs partial molar property. So that is the only equation to satisfy the partial molar property requirement, and we can replace this chemical potential by a more or less familiar term of Gibbs energy. So if we decide to replace the mu I by another partial derivative, then we can see that this d mu I dp, this is temperature composition fixed. Then we try to replace this is exactly the d mu I. So now you can see that we can have the second order partial derivative with respect to g, right? Now we are going to utilize that again. The order does not matter. So what we plan to do is we're going to switch the order. Now we try to take the derivative with respect to pressure first. Then we will take the second order derivative with respect to the component. So what about this term? And keep in mind we are still having this T n as the requirement. So if you want to understand and evaluate this term, we'd better look for the general term of Gibbs energy. dg is sdt, vdp, and those chemical potential terms, right? So dt, that would be 0. because fixed temperature. Compositions are fixed. dmi would be 0. Therefore, dg over dp would be basically nothing but volume, like I have over here, right? So now this term is volume. Now we are going to put the volume back to the second order derivative. So we have dv over dmi, the total volume with respect to component I at fixed temperature, pressure. If I'm looking at the component I, then all the other components are fixed instead of that component I. So that is exactly the definition of partial molar volume. So this is how we have this equation proved. So what's the point of having this this volume? No, this equation. Well, it is quite significant because now if I want to, for example, I want to measure the chemical potential, at least I can design the experiment. I'm going to keep, for instance, the one liquid, one vapor. I can add water. Let's say I'm trying to understand the liquid water, vapor water, this phase equilibrium. In order to understand the chemical potential of water, I can add more and more liquid water. I can try to measure the volume change. Simply because if I add a little bit of extra volume, the new added liquid water will also have the vaporization, will also split into the vapor and liquid and join the new the old system. But I can measure the volume change, right, as a function of the new added moles of water. So basically, the partial molar volume we can measure in the lab. And I take a note of the pressure, take a note of the temperature, then I can have the plot of those points while adding one more of extra liquid, two more of extra liquid, try to measure the total volume, and I can easily prepare a diagram or a plot to figure that out. What would be the chemical potential of liquid water, right? So we were puzzled that we need to satisfy temperature, pressure, chemical potential if we want to tell whether the system is at equilibrium or not. But previously we were puzzled that chemical potential is quite abstract. We don't know how to measure or monitor. But now with this first equation, we actually have the answer, which is we just need to measure the partial molar volume change. In reality, it's more complicated than I just described, but the general idea is exactly as what I just described. We simply do the PVT measurement, and then we have the understanding of chemical potential. Okay, so let's try to take a look at a few more slides. And the following slides are, again, to convince you that we are coming back to the discussion pattern. So we introduced the concept of chemical potential. We have demonstrated the use of chemical potential, which is the criteria to determine if the system is at equilibrium or not. We moved on to have the equation for chemical potential, which is coming from the definition. And now here we have a working general equation to measure, to determine the chemical potential. What's the next? The next is let's do some demonstration on the simplified systems. And of course, the most simple system is ideal gas, right? Remember that when we introduce chemical potential, That is for all the components in all the phases, gas phase included. So when we have the gas phase, we are able to measure or calculate the chemical potential in the gas phase. How do we measure? Well, the equation is a partial molar volume. Then we need to figure out what is the partial molar volume. If I have that quantity, then that is the same value of my chemical potential to that component. So now when we talk about the partial, because I have to take the partial derivative with respect to number of moles. So here it's more convenient to include those number of moles. So now that is the total volume. It's not PV equals RT. Previously, we tried to talk about the volume as a specific volume, but for the chemical potential discussion, for the partial molar volume discussion, it's more convenient to use the total volume. So if this is PV, we are going to have number of J components, so each will have the number of moles, then PV is MRT. And then we try to have the total volume, and then we are ready to take the partial, we are ready to take the dV over dMi, looking at a specific item, right? While keeping temperature, pressure, other components. If I have M prime, meaning only the I component is changed. And that itself is, we can replace that by a much easier term with a hat. That is related with mu I over dP, no, d mu I, sin Tp. M prime, right? So those was those terms were on the previous slide. So let's move on to see what I have. So now we try to have this is the equation we have. Now if you try to look at R is a constant, T is a constant, P is a constant, so we can have PVT. And also when you have, say, N1 plus N2 plus all the way dot 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 plus Mi plus Ni.
Dr. Paul,
Yep.
is there any difference between the Ni and the Nj?
Yes, I'm trying to trying to explain it right now. So here, when we have N1, N2, Ni plus 1 dot dot dot, those would be the number of moles. Think about the example I have with CO and oxygen. Okay. So here, let's say N1 represents CO, N2 represents oxygen, Ni, at some case, I'm going to use this as nitrogen. So there you can see that they are independent of each other, right? Those would be simply the other components or the other species. So this is why if you take the partial derivative of this term over dMi, then we can realize that, well, dN1 over dNi is 0 because CO has nothing to do with nitrogen. They are independent of each other. So I'm going to have lots of zeros because those species, they are independent of each other. The only non-zero term would be this one, right? dmi over dmi is 1. All the other terms would be 0. So this is why now if you try to take a look at this term, we have this PVT would be constant, so I can move them outside of the partial derivative term. And over here, when I have this d summation of j from 1 to m, then take the derivative with respect to ni, this is just 1. That is my answer. So 1 multiplied by RT over P. This is why this is my final answer. Okay. I guess I have to stop almost over here. Let me have 1 more minute to finish the equation. So try to come back to take a look at what's going on for those multiple terms and their partial derivative. So if we move on, then we have received this term, then this is purely to replace and utilize the fact that this equals Vi with the head, partial molar volume. So if I have this term, then we are going to replace the left-hand side by d mu I over P temperature. Now this is ideal gas. It's RT over P. Now you can see that I have d mu I have dP. And on the right-hand side, I have the pressure term. So I'm going to manipulate this further by, number 1, I can divide on both sides by Vi. So if I divide this by 1 over Vi, no, Yi, this is Yi with the denominator, then this is a partial pressure of the I component. This Yi, put it inside, I'm going to have d partial pressure of that I component. And I have the last slide of today's lecture. So we try to have this to replace the Pi, then we are going to move this term back to the right. So now you have the full derivative, d mu I over the ideal gas is corresponding to RT d log of the partial pressure. Once we have that, that should be straightforward. Now moving forward, we can take the integration for this equation too. All right, I'm planning to stop here and we will pick up the other slides at the beginning of Tuesday. Then we will switch back to chapter 7, 8, and 9. I'll have the reading assignments out later today. Any question before you guys leave?